Before we start, yes, we know what Uranus sounds like. We're going to say it anyway, multiple times, professionally. The solar system has a rule, a simple, obvious, seemingly unbreakable rule. The farther you are from the sun, the colder you get. Mercury bakes, Pluto freezes. Everything in between follows that gradient more or less, except it does not always. Venus is hotter than Mercury, even though Mercury is the closest planet to the sun. Distance from the sun does not tell the full story. But the Venus-Mercury case is relatively well known. There is a far stranger violation of the rule hiding in the outer solar system, one that does not involve atmosphere trapping heat or greenhouse gases or anything so elegant. Uranus, the seventh planet closer to the sun than Neptune, is colder, not by a negligible margin. Its minimum recorded temperature of minus 371 degrees Fahrenheit makes it the coldest planet in the entire solar system. Neptune, sitting a billion miles further from the sun, is measurably warmer. In this video, we will find out why. The answer involves internal heat, an ancient catastrophic impact, and one detail that planetary scientists still cannot fully explain, even after decades of study. First, the facts. Uranus sits at an average distance of 1.8 billion miles from the sun. Neptune sits at 2.8 billion miles away, more than a billion times further out. By every simple model of planetary temperature, Neptune should be the colder of the two. It's not. The minimum recorded temperature on Uranus is minus 371 degrees Fahrenheit. The minimum recorded temperature on Neptune is minus 353 degrees Fahrenheit. Uranus is colder by 18 degrees Fahrenheit. For a comparison involving two planets a billion miles apart, that gap is not noise. It is a real and consistent anomaly. When Voyager 2 flew past Uranus in 1986 and Neptune in 1989, the only spacecraft to ever visit either planet, the contrast was immediate and dramatic. Uranus appeared smooth, featureless, almost inert. Neptune was alive, massive storms, bright cloud streaks, a great dark spot the size of Earth, driven by the most powerful sustained winds measured anywhere in the solar system, up to 1,200 miles per hour. Two planets of similar size, similar composition, similar distance from the sun, and yet one appears switched off while the other rages. The reason for that difference is also the reason for the temperature anomaly. To understand what is happening, we need to talk about a source of warmth that most people never think about: the heat that planets generate internally. Every large planet in our solar system was formed from an enormous cloud of gas and dust collapsing under its own gravity. That collapse released enormous energy that has been slowly radiating outward ever since. On top of that, the outgoing gravitational compression of a planet's interior generates continuous heat. The result is that large planets are not just warmed by the sun, they are also warmed from the inside. Jupiter radiates roughly twice as much heat as it receives from the sun. Saturn does the same. Neptune emits about 2.6 times more energy than it absorbs from sunlight. This internal heat drives the convection that creates Neptune's furious weather, the storms, the cloud systems, the supersonic winds. Uranus emits almost no internal heat at all. Its energy output is very nearly identical to the amount of sunlight it receives. It is the only giant planet in our solar system that does not appear to have a significant internal heat source. Its atmosphere is not being driven from below. It has no powerful convection, no planet-wide storm systems, no fury, just a smooth, cold, almost dead exterior. Without that internal warmth, Uranus's atmosphere has nothing to keep it above the baseline temperature set by the faint sunlight it receives at nearly 2 billion miles from the sun. And that baseline is extremely cold. Enjoy deep fact-check space stories? Hit subscribe and activate the notification bell. Otherwise, YouTube will not show you the next videos, and you'll miss what we uncover next. So why does Uranus have almost no internal heat? Why is it the only giant planet that appears thermally dead? The leading explanation involves a catastrophe that happened billions of years ago and left a permanent mark on everything about the planet. Uranus spins on its side. While Earth has an axial tilt of about 23 degrees, Uranus is tilted at 98 degrees. It does not spin upright like a top. It rolls through space like a bowling ball, with one pole facing the sun for 42 years at a time, while the other sits in continuous darkness, and then the situation reverses for the next 42 years of its 84-year orbit. Astronomers believe this extreme tilt is the result of a massive collision early in the solar system's history, a planet-sized object striking Uranus with enough force to knock it almost completely onto its side. That kind of impact does not just tilt a planet, it disrupts its interior. The current leading theory is that the impact created a layer of compositional stratification deep inside Uranus, essentially a barrier that prevents the hot interior from convecting upward. On Neptune, heat generated deep inside can rise through the planet and reach the outer atmosphere. On Uranus, that pathway appears to be blocked. The heat is trapped, the surface stays cold, the atmosphere stays quiet. It is as though someone broke the planet's heating system billions of years ago, and the planet has been running on empty ever since. But the tilt alone doesn't fully explain the temperature anomaly, because here's what makes Uranus genuinely puzzling to planetary scientists. The tilt should actually make Uranus warmer in places, not colder. The pole facing the sun for 42 straight years absorbs more solar energy than anything else at that distance, and yet the temperature across the planet remains stubbornly uniformly cold. The mystery goes deeper than a single impact. You would expect Uranus's extreme tilt to produce extreme temperature variations across the planet. The sunlit pole soaking up decades of continuous sunlight should be dramatically warmer than the pole sitting in darkness, but it's not. Observations show that Uranus maintains a remarkably uniform temperature across its entire surface, from the sunlit pole to the dark pole, from the equator to the high latitudes. Everything is roughly equally cold. That uniformity is itself a mystery. On a normal planet, atmospheric circulation would redistribute heat from the warm side to the cold side. But on Uranus, that redistribution appears to be so efficient, or the overall heat budget so low, that even decades of concentrated sunlight on one pole cannot raise the temperature meaningfully above the global average. Some models suggest that Uranus's atmosphere, disrupted by the ancient impact that tilted it, developed unusual zonal circulation patterns. Near the equator, winds blow in the opposite direction to the planet's rotation at around 110 to 220 miles per hour. Closer to the poles, they reverse and blow with the rotation at up to 560 miles per hour. This strange wind structure may help explain how heat gets redistributed so efficiently across a planet that receives almost none from its interior. The result is a world that is uniformly cold in a way that no other planet in the solar system is. Not a cold side and a warm side, just cold everywhere all the time. There is a broader pattern here that Uranus and Venus both illustrate, and it is worth naming directly. We tend to model planetary temperature as a simple function of distance from the sun. The closer you are, the more sunlight you receive, the warmer you are. And at the most basic level, that is true. But planets are not passive objects sitting in sunlight. They are complex systems with their own histories, their own interiors, their own atmospheres, and all of those factors can override the simple distance rule. Venus is hotter than Mercury because Venus has a dense carbon dioxide atmosphere that traps heat through a runaway greenhouse effect. The atmosphere is doing the work, not the distance. Uranus is colder than Neptune because Uranus lost its internal heat, probably through an ancient catastrophic impact, while Neptune retained its. The interior is doing the work, not the distance. In both cases, something other than proximity to the sun is the dominant factor. And in both cases, understanding why requires knowing the history of the planet, not just where it sits in the solar system today. This is what makes planetary science genuinely interesting. The solar system is not a neat gradient. It is a collection of individual worlds, each shaped by events billions of years in the past, each following its own thermal logic. The simple rule, closer means warmer, is a starting point, but the exceptions are where the real story lives. Uranus remains the least explored planet in the outer solar system. Voyager 2 flew past in January 1986 for a matter of hours. No spacecraft has been in orbit around it. No probe has descended into its atmosphere. The entire picture we have of Uranus comes from a single brief encounter almost 40 years ago, combined with what telescopes on Earth and in orbit can observe from billions of miles away. NASA has been studying a proposed Uranus orbiter and probe mission for years. If funded and launched in the early 2030s, it would arrive sometime in the 2040s. And for the first time, we would have a spacecraft circling this strange cold world, measuring its heat flow directly, mapping its interior structure, sampling its atmosphere. Until then, the question of exactly why Uranus lost its internal heat, and whether that loss was caused by the ancient impact, by internal stratification, or by some combination of factors we have not yet identified, remains open. The most anomalous planet in the solar system is also in many ways the most mysterious. The solar system has rules. Uranus breaks them, and it has not finished surprising us. We mentioned Venus briefly in this video, a planet further from the Sun than Mercury, yet dramatically hotter. That contradiction has its own story, and it is just as strange. Watch why closest doesn't mean hottest. Venus Secrets. The answer will permanently change how you think about planetary temperature.